All right, let's start our journey through all these different nucleophiles with oxygen nucleophiles. And the first reaction we study here is taking a ketone or an aldehyde and putting it in water. And what do we get? Well, it says that in the presence of water, a ketone or an aldehyde is going to be in equilibrium with its hydrate. And so you're going to see a lot of new functional groups in this chapter. And so here's our first one, a hydrate. And this is when we have a carbon with two R groups, but the carbon also possesses two hydroxyl groups on it. So that's what we call a hydrate. Now it turns out that when you put a ketone or an aldehyde in water, that the equilibrium actually does not favor the formation of the hydrate. Okay, it's mostly going to lie to the side of the carbonyl. So if I draw new equilibrium arrows, it's actually more like this, mostly by the side of the carbonyl, and you only get a little bit of the hydrate unless it's a very simple aldehyde like formaldehyde. And so this reaction is actually very slow unless acidic or basic conditions are used. And you have to know the mechanism for the formation of a hydrate in both basic and acidic conditions. And so let's start with the base catalyzed hydration reaction, or the base catalyzed formation of a hydrate, either way. So here we have the simplest aldehyde we can have, formaldehyde. We're in base, we're in hydroxide, so we have our nucleophilic attack in our first step. Then we go from our sp2 hybridized carbon to our sp3 hybridized carbon. And of course, there's going to be water in the reaction mixture because a base like sodium hydroxide is dissolved in water, so that's going to act as our acid. We do a proton transfer, and there you go. Now we have our hydrate. Okay, so you have to recognize a hydrate when you see one. Okay, and here's the mechanism for the formation of a hydrate under acidic conditions. Now remember, a hydroxide ion is a strong nucleophile, but water is a weak nucleophile. Okay, so if you want to write next to that, weak nucleophile. So that means water is not just going to come in and spontaneously attack this carbonyl, right? Because remember, the aldehyde carbonyl is electrophilic, but it's only a good electrophile. But if we protonate it with our acid in the first step, we end up with our oxonium ion. And this is an excellent electrophile, isn't it? And now our water, which is a weak nucleophile, can come in. We do our nucleophilic attack. Then water is going to be our conjugate base in our reaction mixture. And it does a proton transfer in the end to give us our hydrate. And so the key to keep in mind here is that when you're dealing with base catalyzed hydration, the nucleophilic attack will be the first step. But when it's under acidic conditions, the carbonyl being protonated, that will be the first step. Why? Because water is a weak nucleophile. And so you want to keep these things in mind when you're drawing mechanisms in this chapter and always. If you're in acidic conditions, so if you're doing a reaction in H3O+, okay, it's okay to draw H3O+, it's okay to draw H2O, but if you draw OH- or something with a negative charge, that is a big no-no. There should be no strong bases existing in an acidic environment. Conversely, when you're drawing a mechanism in basic conditions, it's okay to draw OH-, a hydroxide ion. It's okay to draw water, which is the conjugate acid. But if you start drawing things like hydronium ions or positively charged ions in there, that's impossible. It's not going to exist. So the intermediates that you draw along the way have to be consistent with your conditions. So again, acidic conditions, hydronium, water, positive charges. When you're in basic conditions, hydroxide, water, and anions. Now we saw what happens when we treat an aldehyde or a ketone with water, but what happens if we have an alcohol? So here we have our our ketone, and we have two equivalents of an alcohol, and then we have H+ in brackets. Whenever you see H+ in brackets, that means an acid catalyst. Okay, so we have just a catalytic amount of acid, and we end up forming this brand new functional group here that we call an acetal. Take a look at this thing. The acetal, we have this sp3 hybridized carbon, which is attached to two R groups, but then it's like it's got an ether here. It's almost like two ethers on the same carbon like that, but that's what we call an acetal, and you definitely have to be able to recognize an acetal. Now, keep in mind that this reaction is in equilibrium, so we take our aldehyde or ketone plus our two equivalents of alcohol, And then we end up with our acetal plus water. And that water is going to be important as we study the mechanism in detail. Now, if you're wondering, well, what kind of acid catalyst am I going to be using in this reaction, Mr. Dion? Well, there's two main types of acid catalyst that we use in the formation of an acetal. One is what we call PTSA sometimes. So PTSA, which stands for para-toluene sulfonic acid, okay? Or you can abbreviate it as TSOH. That's a strong acid. And then sulfuric acid as well, which you guys know frontwards and backwards. You've been studying that since General Chemistry 1. So these are both very commonly used as the acid catalyst in the formation of an acetal. Now, if you're wondering why this acid in particular, sometimes this is kind of a strange, very particular acid. I think one of the reasons why is PTSA is a solid at room temperature instead of sulfuric acid, which is a liquid. And this can be very easily recrystallized. And so if you have conditions where you need everything to be very pure, you can crystallize the toluene sulfonic acid very quickly. Now, you really want to study the mechanism of the formation of the acetal. So let's go through it, okay? Now remember, we're starting it with our ketone or aldehyde, which is a good electrophile, but it's not an excellent electrophile, is it? So the first step is going to be a proton transfer to create an oxonium ion, which is an excellent electrophile, isn't it, right? A very powerful electrophile. Now, if you're saying, what's HA+? What is HA+? Well, let's think about what's in our reaction mixture, okay? Let's say we have our strong acid like sulfuric acid. So let's imagine you have sulfuric acid like this, and then you combine it with your alcohol. Well, remember, sulfuric acid is a stronger acid than the alcohol, so the equilibrium is actually going to lie to the side where the alcohol is protonated, like this, okay? So that's going to be the major acid that's present in your reaction mixture. So that is your HA+, okay? The conjugate base is going to be the alcohol that's going to be left over, right? So you're also going to have that plus you're going to have the HSO4 minus ion. So that's what they mean when they say HA+. They just avoid writing the entire structure of the protonated alcohol. But you can include it if you want to. It's totally fine. All right, so now we've protonated it. And so now that we've created an excellent electrophile, now an alcohol can come in as a nucleophile because an alcohol is a weak nucleophile, isn't it? So let's take a look. So after your alcohol attacks, then you go from your sp2 hybridized carbon to your sp3 hybridized carbon. And then you're going to do a proton transfer with the conjugate base of your HA+ here. Okay, that's going to do a proton transfer in order to give you what we call a hemiacetal. Okay, and we're going to talk about hemiacetals in more detail later on. We're going to talk about how they pertain to sugars like glucose. But anyhow, we're still not done yet, are we, right? Because we have to replace this hydroxyl with another OR group. So we want to protonate that to convert it from here. It would be a very poor leaving group. But once you protonate it, then it becomes a very, well, here they put excellent. I'll put good because it's easier to spell. Good leaving group. And so then it's going to get expelled. So we have our loss of leaving group. Then we go right back to having another sp2 hybridized carbon. And so you can see that it's also an oxonium. And so the alcohol, the second equivalent of alcohol, can come in and do a nucleophilic attack. We do a proton transfer, and there we go. So keep in mind that this whole mechanism occurs in kind of two stages, doesn't it? The first stage takes us to the hemiacetal, and then the second stage, stage 2, this stage here brings us to the acetal. And I want you to remember that importantly, in the second half of the mechanism, if you will, this is where we lose the water, okay? Because remember, I told you that the loss of water is going to be very pertinent as we move forward, okay? Also, keep in mind that every single step in this mechanism is in equilibrium. Everything is in equilibrium. So if you're looking at this and saying, well, what's going to drive the reaction forward? Well, we're going to cover that more in just a little bit. And so just like I told you on the previous slide, acetal formation is an equilibrating process. Every step in the mechanism that you saw on the previous slide, every single step was in equilibrium. Every step had this kind of arrow, right? Frontward, backward, okay? So they were all in equilibrium. You notice here, if we take formaldehyde and we treat it with 2 equivalents of ethanol, that in that case, since it's a very simple aldehyde, the equilibrium is actually going to favor the product, the acetal. But if you have a ketone, it tells you right here flat out that the acetal is not favored. And so what are you going to do to push the reaction forward? How can, or put it another way, how can you get the reaction to go in this direction and have almost none of the reverse reaction? Well, in order to do that, we're going to employ Le Chatelier's principle. Now, instead of using 2 equivalents of an alcohol, you saw before we had 2 equivalents of an alcohol. Well, what if instead of that, what if you used a compound that has 2 alcohol functional groups built right into it, okay? And this is what we call ethylene glycol. So ethylene glycol, and you would have seen this compound in the alcohols chapter. Why not use that? Because then you end up with an acetal that is cyclic. You see that this R group and this R group are tied together, so they're tethered together, so we get a cyclic acetal. And sometimes, instead of using ethylene glycol, chemists will use 1, 2, 3, they'll use 1,3-propane diol. And in that case, you would end up with a cyclic acetal as well. And I'll just kind of scribble it in here. But then you'd have 1, 2, 3 carbons in your bridge like that. Well, I told you that the water that is formed as a product in the second step of the reaction, that it was going to be key to pushing the reaction forward. So check it out. The way that we control acetal formation is by adding or removing water. Remember, when you form the acetal, water is a product. And so if you can remove the water, okay, from the reaction mixture, that's going to favor the formation of the acetal. And so when we want to make the acetal, when we want the reaction to go forward, oftentimes we will write minus H2O. And what that means, the negative H2O means water is removed. And there are different ways to remove the water from a reaction mixture, but if you want to look one up, one is using something called a Dean-Stark trap. It's actually an ingenious, or a Dean-Stark apparatus, I don't know. But either way, it's just an ingenious piece of glassware that allows you to distill the water out of the reaction mixture, and that pushes the reaction forward. However, let's say you had your acetal intact and you wanted to remove it. Well, what would you do? Well, since all the steps are reversible, you would just use a vast excess of water and only a little bit of acid, and that would remove the acetal. And so that way, check it out, acetals can actually be used as protecting groups for a ketone or an aldehyde. And so let's say you wanted to do this synthesis here. Check it out. You have a bifunctional compound. You have a ketone, okay? And then you have this ester, and then the ester is being reduced down to this primary alcohol here. Well, you guys all know how to reduce an ester down to an alcohol. What would you use? You do lithium aluminum hydride followed by an aqueous workup. However, what's the problem with that? Is that lithium aluminum hydride would also reduce the ketone, okay? That's not going to work. So what's the solution going to be? Well, you can see it's here on the bottom of the slide. We're going to have to protect the carbonyl first. We're going to protect that as an acetal, and then we're going to reduce the ester down to the alcohol, and then we can just remove the acetal using aqueous acid. So here's our first step. We're going to use our ethylene glycol, catalytic amount of acid. Note that we write minus H2O, which means loss of water, which is going to push the reaction forward like this. So now we have our acetal, and so now our ketone is protected. Okay, protecting group. All right, so now that we have our protecting group installed, then we can reduce our ester using a lithium aluminum hydride. And what's neat about this specific case is that you remember after the reduction with lithium aluminum hydride, you need an acid workup with H3O+, but that would do two things. It would add this proton, but it would also remove the cyclic acetal and bring you the carbonyl back. So it's kind of a 2-for-1 step there. Now I told you to keep hemiacetals in mind, and you remember the hemiacetal, it's like halfway between the hydrate and the acetal. It's got a carbon with an ether and a hydroxyl on the same carbon. I told you to keep those in mind because hemiacetals are actually very difficult to isolate as the equilibrium either favors the aldehyde or ketone or the acetal based on whatever conditions we want to use. But it turns out that cyclic acetals cyclic hemiacetals, which are found in things like carbohydrates. So carbohydrates. Cyclic hemiacetals can be favored when they're in a ring. And so you see that right here. Check out this neat compound. It's got everything built in. You've got your electrophile, you've got your ketone right here, and you have your nucleophile, you have your hydroxyl in the same ring. So if you put that in a catalytic amount of acid, what's going to happen in the first step is that this is going to be protonated to give you the oxonium ion, and then the alcohol can come in and function as a nucleophile like this. And I haven't drawn the whole mechanism, but after a couple of proton transfers, then you're going to end up with this cyclic hemiacetal. And you remember that in organic chemistry, 1, 2, 3, 4, 5, 6-membered rings are highly favored. And the reason that this is important is because carbohydrates, like glucose, actually are hemiacetals. Check it out. If you look at glucose, you see this carbon has OR on it, and then it has OH here. And so this is a cyclic hemiacetal. Glucose, which is the most common sugar on the planet. All right, question 19.8 asks us to draw a mechanism for this transformation. So we're forming an acetal from this cyclopentanone, and we're using a catalytic amount of sulfuric acid, and then we have excess methanol. So that just means we have more than enough methanol to do the reaction. But before we even start the mechanism, I want to remind you that when you combine your sulfuric acid, I'll use a black pen, when you combine your sulfuric acid plus your methanol, like this, there's going to be equilibrium that lies to the side of the protonated methanol, right? So you're going to have your protonated methanol like this, and then you're going to have your HSO4 minus ion. Since the equilibrium is going to lie to the right, this is going to be the major acid. Okay, and this is its conjugate base. And so I'm not going to use sulfuric acid to do the proton transfer here. Technically, you could, because there's still going to be some sulfuric acid in the equilibrium, but the acid that I have in the yellow circle is going to be present in a greater amount, and so this is what I'm going to use as my acid. So I'm going to delete all this just to get us started here, and we'll start by drawing the structure of the protonated methanol. Instead of writing Me, here I wrote CH3. Remember, CH3 is the same thing as a methyl, like this. Anyhow, so the first step is going to be a proton transfer. So let me zoom in a little bit here. So we're going to take this good nucleophile and we're going to make it a great or an excellent nucleophile. Keep in mind this step is going to be in equilibrium. So let's draw our protonated oxygen, or our oxonium ion. And so now this is going to be an excellent electrophile. And so now our methanol, which is the conjugate base, right? After this guy loses its proton, what's left over? Methanol. So now methanol can come in as a nucleophile. So we're going to get nucleophilic attack like this. And then we're going to draw the intermediate that results. So we're going to end up with our hydroxyl group in place, like this, and then we're going to have our OCH3, but it's going to be protonated. And so in order to get to our hemiacetal, we need to do another proton transfer, and of course there's going to be more methanol in the equilibrium to function as a base. Remember, we're in strongly acidic conditions here, so methanol can function as a base. And so at this point, now we're going to have our hemiacetal. So we have our OH group and our OCH3 group. And so this is our hemiacetal, like this. Now remember, in the second step, we have to lose water. So we have to take this hydroxyl, which is a poor leaving group, and convert it into an excellent leaving group. So we're going to have to do a proton transfer. So we're going to need more of our acid. So we'll draw in our acid like this. Okay, we'll do our proton transfer to make that excellent leaving group. And so it's going to look something like this. So I'm just going to condense it a little bit here. I'll put OH2, positive charge. Then I have my OCH3 like this. Now, when my leaving group leaves, keep in mind, this is my leaving group. In order for it to leave, I have to reform my sp2 hybridized carbon. And so I'm going to form my new pi bond, and I'm going to eject the water like this. So Once I do that, I'll put here minus H2O, so that's the loss of my water. And now I have my sp2 hybridized carbon again. Now I still have an excellent electrophile, so now methanol can come in as a nucleophile. You can see I'm kind of grasping for space here, aren't I? Anyhow, so now my methanol is going to come in, do a nucleophilic attack, and I'm going to be very close to the end. So I'm going to have my OCH3 group here. Now I've got OCH3 here as well, but it's protonated, isn't it? Right, so it's going to have a positive charge. And so to get to the final product, the very end of the road, what's going to happen is my methanol is going to come along and it's going to pull off that acidic proton. And there you go. That's the end of the mechanism. So notice you started out with the protonated methanol as your acid, and in the last step, you reform the protonated methanol, right? So it's a catalyst. It keeps getting recycled over and over. So make sure you know how to draw the mechanism of acetal formation. All right, next question. Propose an efficient synthesis for each of the following transformations. In A, you can see that we need to add 2 carbons here, but we know there's an acidic proton here, so we could abstract that with sodium amide and then treat it with ethyl iodide. That's just some alkyne chemistry. The problem with that is sodium amide is also a good nucleophile, so that would come in and attack here, and that would destroy the carbonyl. And so what's the first thing we need to do is we need to protect that carbonyl. So we're going to protect that as an acetal, and I'm going to choose to protect it as a cyclic acetal. So we'll start with our carbonyl. Let me see here. Where's a good place to start so I don't run out of space? So we're going to take our carbonyl compound. We're going to treat it with ethylene glycol. We're going to use a catalytic amount of acid, and we are going to remove the water, and that's going to give us our cyclic acetal like this. Now we can abstract our proton using our sodium amide, add our electrophile, which would be ethyl iodide in this case, and that is going to add those 2 extra carbons we need. And we still have our cyclic acetal intact. And then the last step, I'll just draw it as an arrow to the product like this. That would just be some aqueous acid, and that would remove the cyclic acetal. All right, in the next one, in B, we have a ketone and we have an ester. And you can see that we're doing a Grignard on the ester. We're adding 2 equivalents of phenyl magnesium bromide, so excess phenyl magnesium bromide, followed by an aqueous workup with acid. However, you know that Grignards, if you had phenyl Grignard, right, it's going to react with this carbonyl as well. And so we need to protect it as a acetal. So let's get started. And I'm going to redraw the compound like this. So there's our ester. Yep, looks good. So the first step is just practicing doing what we did in the last problem. I'm going to use ethylene glycol, aqueous acid, and I'll put here subtract H2O. That's going to give us our cyclic acetal. Then our ester is going to be intact. So now, to make that tertiary alcohol, we're going to treat it with excess phenyl magnesium bromide, and then H3O plus. But keep in mind that the H3O plus is not only going to add this proton, but it's also going to remove the cyclic acetal at the same time. And so really, that's all we need to do is just that last step, and that's going to be the end game for the entire thing, and that's going to give us the product. So didn't have to draw a whole lot for this one. And there you have it.